NaF plus SCN in backward reaction, NaSCN plus F negative. Conceptually, NaF is formed through hard-hard interactions. Thus, according to HSAB theory, the reaction is preferred in the backward direction. OH negative is much stronger base than SO3 negative and hence cannot be displaced by weaker base SO3 negative. This reaction, however, is favored by HSAB principle. CH3CdOH plus SO3 negative in equilibrium with CH3CdSO3 negative plus OH negative. It is important to conclude at this stage that Lewis acid-Lewis base reactions are governed by two independent principles, viz. First, strength of the acid and base, 2. Softness and hardness of acid or base. The definition of hardness primarily uses the idea of polarizability, which states that a less polarizable species is hard and a more easily polarized is soft. For ions of similar charges, the ratio of charges to radius should be used to assess the relative polarizability or relative hardness or softness. However, HSAB principle does not take into consideration the quantitative idea of relative hardness or softness of the species. In summary, the major limitations of HSAB principle are: HSAB principle is too general and without any qualitative scale of measurement. 2. HSAB principle does not take into consideration the acidic or basic character of the compounds. 3. HSAB principle fails to explain the feasibility of the reaction. CH3 positive gas plus H2 gas gives CH4 gas plus H positive gas. Delta H is equal to 86 kilocalorie per mole. In spite of the soft CH3 positive H negative interactions, it is probably the greater acidity of proton H positive relative to CH3 positive gas cation that is responsible for the unfavorable reaction. Article 4.5 Limitations of HSAB principle. The hardness and softness of an acid or a base is primarily related to stability of the hard and soft interactions. It has no concern with the acidity or basicity of the acid or base. For example, OH negative and F negative are well known hard bases. However, the basicity of hydroxide ion OH negative is very large as compared to the fluoride ion. In fact, the basicity of hydroxide ion pKa is equal to 15.7 is approximately 10 raised to the power 13 times that of fluoride ion. pKa is equal to 2.85. A strong acid or a strong base is well known to displace a weak acid or a weak base. For example, the reaction between a sulfite ion and hydrogen fluoride proceeds in the forward direction. It means that the stronger base SO3 negative can easily displace the weaker base F negative ion from the acid hydrogen fluoride. However, the above reaction is not favored according to HSAB principle as detailed below. SO3 negative plus HB gives HSO3 negative plus F negative, which only favors hard and soft interactions. Similarly, a very strong base OH negative can displace a weak base from a soft acid methyl mercury 2 ion. OH negative plus CH3HgSO3 negative in equilibrium with CH3HgOg OH plus SO3 negative. K equilibrium is equal to 10. Reaction 4.2. However, the above reaction is not favored according to HSAB principle, which only favors hard or soft interactions. In both the above cases, 4.1 and 4.2, it is the inherent strength of the bases SO3 negative greater than F negative and OH negative greater than SO3 negative that forces the reaction in the forward direction in spite of less preferred formation of hard soft pairs in the product. This is true in cases especially when the inherent strength of bases or acids being compared are significantly different. The order of the basic strength being OH negative 15.7 greater than SO32 negative 5.8 greater than F negative 2.85. In other words, significant different basic strength forces the reactions 4.1 and 4.2 against the wishes of hard soft interactions. However, when both the strength of the acids and bases and hardness softness are not significantly different, then HSAB principle works well, resulting in products having hard and soft combinations. For example, CH3HGF plus HSO3 negative in equilibrium with CH3HG SO3 negative plus HF. K is equal to 10 raised to the power 3, reaction 4.3, and CH3HGOH plus HSO3 negative in equilibrium with CH3HGSO3 negative plus HOH. K is equal to 10 raised to the power 7, reaction 4.4. It is important to mention that the inherent strength of acids and bases should not be ignored while applying HSAB principle. Article 4.6 Symbiosis. The hardness or softness of an acidic or basic center is not an inherent property of an atom but depends upon the substituents. Thus, ammonia is a hard base while pyridine is a borderline base. The acidic B3 positive ion is borderline between a hard and a soft acid. Addition of three small sized non-polarizable substituents like fluoride ion F negative make it a hard Lewis acid BF3, whereas addition of electron donors and easily polarizable groups like hydride ion H negative makes a soft Lewis acid BH3. The difference in the hardness and softness of BH3 and BH3 can be illustrated nicely in the following examples. R2S FBF3 plus R2O gives R2O BF3 plus R2S. R2O BH3 plus R2S gives R2S BH3 plus R2O. Jorgensen in 1968 observed that hard ligands have a tendency to combine with a metal ion having hard ligands, and soft ligands have a tendency to combine with the metal ion already having soft ligands. He coined a term symbiosis for such interactions. The hard BF3 molecule prefers to continue with hard base F negative ion to form tetrafluoroborate BF4 negative, whereas soft acid BH3 prefers to combine with soft base H negative ion to give tetrahydroborate BH4 negative ion. BF3 plus F negative gives BH4 negative. BH3 plus H negative gives BH4 negative, or B2H6 plus 2H negative gives 2BH4 negative. An important outcome of symbiosis is that symmetrical substituted compounds are formed in preference to the unsymmetrical substituted compounds. For example, compounds containing mixed substituents interact strongly to yield symmetrical compounds with the base substituents as given below. BH3F negative plus BF3H negative gives BH4 negative plus BF4 negative. Similarly, mixed fluorinated methanes react to give symmetrical methanes. CH3F plus CF3H gives CH4 plus CF4. In brief, symbiosis can be defined as the tendency of soft ligands to combine with the metal ion already having soft ligands, and tendency of hard ligands to combine with the metal ion already having hard ligands. Article 4.7 Theoretical basis of hardness and softness HSAB principle. A number of theories have been proposed to explain the preference of hard acids towards hard bases and soft acids towards bases. First, electrostatic interaction theory. According to this theory, hard acids and hard bases form purely ionic compounds. Therefore, hard interactions are purely ionic or electrostatic. Most of the hard acids such as Li positive, Na positive, K positive, etc., and hard bases such as O2 negative, F negative, and OH negative, etc., are well known to form ionic compounds. We know that the electrostatic energy of an ion pair is inversely proportional to the interatomic distance. It means the smaller the ions, the smaller will be the internuclear distance, and hence greater will be the electrostatic energy between the ions. As a result, the final compound formed by hard acid and hard base will be highly stable. Second, polarization power and polarizability. Electrostatic interactions cannot explain the soft interactions because of the bigger size of the soft ions. Therefore, the interactions between large sized acids and bases must involve covalent character. For example, soft acids such as Ag positive, Hg positive, Cu positive, etc., form strong compounds with soft bases like S2 negative, I negative, etc., which have substantial covalent character. Almost all the soft acids have 6 or more d electrons. Soft acids with D10 configuration are excellent soft acids. Example Ag positive, Hg2 positive. It is these d electrons that have more polarizing power. Secondly, the soft bases like S2 negative and I negative are easily polarizable. Thus, bonding between soft acids and soft bases is largely covalent. Natural occurrence of ores and minerals. The natural occurrence of ores or certain metals can be easily explained on the basis of HSAB principle. Hard acid metal ions such as Mg2 positive, Ca2 positive, Al3 positive, Fe3 positive, Cr3 positive, etc., frequently occur as their oxides, fluorides, or chlorides and carbonates. This is primarily due to their preferred hard base interactions. We know that oxides O2 negative, halides F negative or Cl negative, and carbonates CO3 2 negative are all hard bases. These hard acid metal ions cannot occur as sulfides because S2 negative is a soft base and cannot form stable compounds. On the other hand, soft metal ions such as Cu positive, Ag positive, Cd2 positive, Hg2 positive, Pd2 positive, etc., occur invariably in ores as their sulfides due to soft acid soft base interaction that result in the formation of stable complex. Interestingly, the borderline acids like CO2 positive, nickel 2 positive, Pb2 positive, zinc 2 positive can occur both as sulfides, soft base, as well as their oxides or carbonates, hard bases, as a result of their intermediate character. 4. Catalytic poisoning. All metal atoms, that is, metal atom in zero oxidation state, are soft acids. Some of the metals, namely vanadium, chromium, nickel, palladium, platinum, molybdenum, etc., are well known catalysts. These metal catalysts have been found to be easily poisoned by soft bases with carbon monoxide, unsaturated hydrocarbons, olefins, alkynes, dienes, and arenes. Organophosphenes R3P and organoarsines R3AS, etc. This poisoning is attributed to the soft acid soft base interactions between the metal atoms and the soft ligands. In fact, these soft ligands are absorbed strongly on the surface of the metals and block the reactive sites by forming metal complexes. In other words, the metal atoms lose their reactivity and are said to be poisoned. Thus, Soft base is complex with the metal in atomic state will act as poisons towards metal catalysts. Article 4.8 Electronegativity and hardness softness. Hardness and softness are related to electronegativity. Species with higher electronegativity values are assigned greater hardness, and those with lower electronegativity values are assigned greater softness. Electronegativity conventionally means the power of an atom in a molecule to attract electrons towards itself. However, in this case, it refers to the power of an individual ion participating in a reaction. For example, lithium atom is known as highly electropositive or lowly electronegative metal, but the cationic species lithium positive with very high second ionization potential has a greater tendency to attract electrons towards itself. As a result, lithium is considered to be more electronegative and hence is a hard acid. On the other hand, heavier transition metals ions in low oxidation states like Cu positive, Ag positive, Hg positive, Cd positive, etc. have relatively low second ionization potentials and consequently possess low values of electronegativity. As a result, these ions are considered as soft acids. Using the same concept of electronegativity, we can define hard and soft bases. This relationship between hardness and electronegativity can explain several important features as to why. First, trifluoromethyl group is a harder compound to methyl group. 2. Boron trifluoride BF3 is harder compared to borane BH3. 3. Ammonia NH3 is harder than trimethylamine CH3 3N. 4. Trifluorophosphine PF3 is harder than phosphine PH3, which in turn is harder than trimethylphosphine CH3 3P. Mulliken-Jeff defined electronegativity psi as a linear function of the partial charge delta developed on an atom according as psi is equal to A plus B delta, where A electronegativity of the atom, B rate of change of electronegativity with charge. The electronegativity value A of the atom is similar to that of Pauling or Allred-Roschow, and the parameter B is called charge coefficient. Small hard and non-polarizable atoms have higher values of B, whereas large soft and polarizable atoms have smaller values of B. Parr and Pearson introduced a new term called absolute hardness, eta, for neutral as well as charged species and correlated it with absolute electronegativity psi. The absolute hardness eta is defined as one half the difference between ionization energy and the electron affinity. Eta is equal to I minus A by 2, where I ionization energy, A is equal to electron affinity of the species in question. We know Millikan's definition of electronegativity is psi is equal to I plus A by 2. The hardness of a base B and acid A may be given as eta B is equal to eta species B positive is equal to 1 by 2 bracket IB positive minus AB positive bracket close, and eta A is equal to eta species A is equal to 1 by 2 bracket IA minus AA bracket close. In order to understand as to why in the equation 4.6 the base B is represented as B positive, whereas in equation 4.7 acid A is represented as such A. Let us consider the interaction of acid A and base B to form the compound AB as A plus B gives AB, A delta negative, B delta positive. In the formation of compound AB, electrons will move from B to A, which is indicated by partial delta positive and delta negative charges. Hardness of B refers to a species going from delta positive to a charge 1 plus delta positive on ionization, while hardness of A refers to a species on ionization from delta negative to a charge 1 plus delta negative. If the shift of charge delta is taken at equal to 0.5, then the charge on B becomes 1 plus 0.5 is equal to 1.5, and on A becomes A 1 minus 0.5 is equal to 0.5. Thus, charge on B changes from 0.5 to 1.5 with an average is equal to 1 by 2 into 0.5 plus 1.5 is equal to 1, and that on A changes from minus 0.5 to 0.5 with average is equal to 1 by 2 into 0.5 minus 0.5, that is equal to 0. That justifies the reason why species B is shown as B positive and A as neutral in equation 4.6 and 4.7. The hardness parameter eta and absolute electronegativities psi of some atoms are compiled in table 4.3. For hydrogen atom, I is equal to 13.59, A is equal to 0.75, psi is equal to 7.17, eta is equal to 6.42. Lithium, I is equal to 5.39, A is equal to 0.62, psi is equal to 3.00, eta is equal to 2.38. Boron, I is equal to 8.30, A is equal to 0.28, psi is equal to 4.29, eta is equal to 4.09, and so on. Hardness parameters of some Lewis acids and Lewis bases are given in table 4.4 and 4.5 respectively. Table 4.4 hardness parameters eta A for some Lewis acids in electron volt. Ions H positive. IA is equal to infinity. IA 13.59, psi A infinity, eta A B infinity, and so on. For molecules, I2 9.3, IA 2.6, psi 6.0, and 3.4 NAB, and so on. Hardness parameters eta B for some Lewis bases in electron volt is given below in the table. A close inspection of the table 4.4 and 4.5 reveal that the absolute hardness values are in good agreement with their known chemical behavior. Hydrogen is the only exception which is different in all the three tables 4.3 to 4.5. It is advisable to consider it as a special case. With the exception of H negative, the values of hardness parameters of all other bases are as expected. The hard bases F negative and OH negative have larger values of NB, while the soft bases SH negative and CH3 negative have smaller values. The hard acids such as Na positive, Mg2 positive, Al3 positive have large Na values, whereas the soft acids such as Ag positive, Cu positive, Au positive have small eta A values. Borderline metals ions such as Mn2 positive, Fe2 positive, Ni2 positive, Cu2 positive, and Zinc2 positive have intermediate values. It is interesting to note down that a column in the periodic table from Mg2 positive to beryllium 2 positive, there is a steady increase in the softness. Similar observations of the softness is made in going from nickel 2 positive to lead 2 negative. There is also an expected increase in hardness values with increase in the oxidation state as Fe0 3.87, Fe2 positive 7.30, Fe3 positive 13.10. However, there are certain discrepancies as well. For example, Ti positive 7.2, Ti3 positive 10.5. The Na value of Ti3 positive suggests it to be a harder acid, whereas Ti3 positive is well known to be chemically softer. However, a comparison of Ti3 positive with other trivalent ions shows the expected soft character. Soft acids are generally transition metals in low oxidation states containing loosely held d electrons. These electrons can be easily donated to ligands. On the other hand, soft bases are pi bond acceptors such as CO, phosphines, R3P, alkenes, and alkynes. In soft acid base interactions, pi bonding is very important. Sigma bond formation due to donation of electrons from the base to the metal is reinforced by pi back bonding from the metal to the base. Article 4.9, Relation to Molecular orbital theory. Molecular orbital theory is a powerful tool to explaining structure and bonding, visible UV spectra, and detailed mechanism of chemical reactions. The concept of absolute electronegativity and hardness can be explained using molecular orbital theory. The ionization energy is a measure of the energy of the highest occupied molecular orbital, HOMO, whereas the electronegative affinity is a measure of the energy of the lowest unoccupied molecular orbital, LUMO, with the change in sign for a given molecule. According to Koopman's theory, E homo is equal to minus I, E LUMO is equal to minus EA. The hardness and softness depends upon the average gap between the HOMO and LUMO. The combination of soft acid with soft base is analogous to the situation in which LUMO of the Lewis acid has about the same energy as the HOMO of the Lewis base. The combination of orbitals resulting in greatly reduced energy for the electron pair coming from base as shown in figure 1.2, thus giving a strong covalent bond. For the hard acid and hard base, there is a greater mismatch of LUMO and HOMO energies, so that there is little energy advantage to be gained from orbital interactions. Figure 4.2b. Thus, covalent bonding will not occur to any significant extent and an ionic interaction will result instead. Thank you.